analysis from singular integrals to function space, to Leibniz rule, and fractional derivative. So Rodolfo.
Okay, thank you very much. I'm trying to find the file and share the screen.
Okay, good.
Let's see, we should also change
The screen now, right?
Yeah, but the view, I want to have the full screen mode. Okay, can you all see?
Yeah.
Oh, what happened here?
But it's not full screen though.
Oh, so maybe now? Maybe now?
Yeah.
Okay. So thank you again for the invitation, Wilfredo, to give these two talks, and I recognize some of you from this morning. So, but maybe there's someone new in the audience. So this is kind of, this is more about mathematics than what we discussed today. What different kind of topics involved this morning, but I'll try still. So it doesn't require having attending the first talk. It's completely self-contained, but I wouldn't say self-contained, but at least it doesn't require the previous talk. And I'll try to start from basic thing as much as I can, but we will move then to more advanced topic. I hope there's something for everybody. So it's not working. Oh, here we go. So again, what is Fourier analysis? Is this prism is the best analogy I can always find to describe what Fourier analysis does. It's a way to take some information in analogy to this prism, the incoming light, and transform it, see how it's built up from other components. In the case of light, wave of different wavelength or different color. And through that process, try to decipher some pattern, some information that is hidden in the signal or function. And the nice thing about Fourier analysis is that you can reverse this process. Once you have all the components, you can get back to your initial signal too. So mathematically, this, I think probably all of you have been familiar with Fourier series, which we write in terms of sine and cosine, or just for convenience, we use exponentials. It's essentially, it is the same thing, but it's just for a convenient way to write it in terms of complex exponential instead of sine and cosines, right? And I won't discuss in what sense we are representing this function and so on, but in a very general sense, we can represent fairly large group of functions by their Fourier series. But one important thing to remember is that, and you may have seen this in some elementary course in partial differential equation, that using separation of variable, how you can solve the heat and the wave equation using a Fourier series. The secret behind this is that what is going on is that the sine and cosine are eigenfunction of this second order differential operator. And that is what make many of the things work. So likewise, we're going to be working in Rn, so in n-dimensional Euclidean space. So instead of Fourier series, we're going to be looking at Fourier integrals, which I choose to define in the way represented on the screen. And the thing is that one important property like Fourier series with this differential operator, ordinary differential operator, is the same here with the Fourier transform. It diagonalizes operators in the sense that it transforms derivatives into I don't know if you can see something appear on my screen. Sorry. Okay. So as I was saying, it transforms derivative. If you take the derivative of a function and take the Fourier transform, it transforms that into a polynomial time the Fourier transform of the function. So this is a crucial property of the Fourier transform, and something that we like a lot and use a lot, because it changed a very difficult analytic operation into something very algebraic, much easier to understand, right? And the notation here, since we work in Rn, is that alpha is typically a multi-index, and for a multi-index, kind of size of alpha means the sum of the entries of these non-negative integer vector. And of course, d alpha, we can have derivative in n different variables. So d alpha will denote alpha 1 derivative in the first variable up to alpha n derivative in the other variable. And the same with C here is a vector in Rn, C to the alpha is this expression here, where C1 up to Cn now are one-dimensional variables, right? Okay, so it also diagonalizes translation invariant operator, and what that means is if we look at convolution operators, so integrate a function against the translate of another one, you take the Fourier transform that, you simplify this operation by getting just the product. So again, a very complex analytic expression gets much simplified on the Fourier transform side. And that's how we like to refer. We like to think there's two sides, the time or space side where the function lives, and the frequency domain where the dual variable, the frequency, lives. And in that domain, a convolution gets transformed into the product of the Fourier transform of the two functions. So here it's a cartoon. There were some cartoon this morning. Here's another one. So this can be used as a way of filtering signals. So here I have a function f in red, which has some predominant shape and then all this noise around it. And I take the Fourier transform, so I move to the other side. This is the frequency domain, and I get the Fourier transform. That's another function, red here. And then I divide this into two sections, or I'm, make this decomposition. I take a function that is one on a small interval around the origin. We speak of that as a low frequency filter, and then we took one at higher frequency that is supported on two intervals away from the origin, or if we were in n dimension, it will be an annulus around the origin. And so each component gives me some information about the function. So if I multiply by the function phi now, since this function is 0 outside this interval, all the other pieces of the function get eliminated. If I go back, this is the general shape of the function I get, and then all the other high oscillation parts are recovered by convolving with a function that is supported away from the origin. And then we multiply by that function, we kill all the low frequency information, and when we transform back, this is what we get. And of course, we add these two pieces, we get the original function. Okay. And this will be used a lot, maybe not so explicitly, but it's embedded in many of the things that we will be talking about. So we also, something very useful in Fourier analysis, that it take advantage of symmetries. And I like this quote a lot by Anthony Knapp that said that the essence of harmonic analysis is to decompose a complicated expression into pieces that reflect the structure of a group action when there is one, and the goal is to make some difficult analysis more manageable. So what do we mean by symmetry? We're talking in this case about translations and dilations, and so they get transformed in a very peculiar way by the Fourier transform. Translation get transformed into modulation, so there's a phase change here, and then dilations take a very particular form too. You dilate a function so that the area under the graph, sort of the L1 norm, the integral of this function, remain constant, but it gets spread out on the Fourier transform side in this way. Okay, so changing for a little while kind of topic. This is not really Fourier, the aspect of Fourier analysis, but it's more general. So we want to look at discrete representation of functions and operators that we'll be looking at. And so think for simplicity, although it doesn't have to be a Hilbert space, think of a Hilbert space and an orthonormal basis for that Hilbert space. But it doesn't have to be like that. Anyway, suppose you have that and that you can represent every function as a superposition of some kind of basic element, phi lambda. And then let's say you have an operator, and I'm not going to discuss continuity or anything like that this stage, but it's just using the linearity of the operator. You apply T at F, and then, you know, let's hope it's a function in the same space. So you can use the basic representation. And then you span F by this expression. I'm doing 2 steps at a time. And then use the linearity of TF. So imagine you move T, pass through the sum to the phi lambda. And then you are now ending up now with 2 sums. And this representation for T of F, which is nothing more than, although this may be infinite dimensional, what we do in linear algebra, we are associating to a linear operator T the corresponding metric in a basis of function. So that's all what we're doing here, except that this metric now could be infinite dimensional. And what we want, you know, learning from the usefulness of the Fourier series and the fact that having eigenvectors of the particular operator will be used. So we want to T to be such that, or the function's phi to be such that they're kind of preserved by T. So I'm not being precise about the, and we will come back to the, but essentially they are eigenfunctions. They are not, and it will take some effort to make that precise, but that's the idea behind. We want T to preserve this kind of basic element. And so, and if there's some orthogonality between the phi lambdas, then the entries of these metrics, maybe they're not quite 0, but they are very small if lambda and nu are very different in some sense. If, you know, if it will be a perfect orthonormal basis of eigenvector, then of course this will be 0 unless delta is equal to, sorry, lambda is equal to nu, but we don't hope for that much, but we have a metric that will be kind of almost diagonal, if not diagonal. So we can do the same because we're going to be looking at bilinear operators. So these are linear operators that are linear in each entry, but we can do the same thing that I just described, and let me go fast over that. And so now, instead of arriving to a metric, we have something that we can call it a tensor that depend on 3 of the basis element. But the same notion we have here, that we want these to be very small, this tensor to have components that are almost neglectable for many practical purposes if the functions that we're using, the indices, you know, identifying this function are very far apart. Now, the difference of what we will be doing is that instead of using pure tones, so the complex exponential of Fourier analysis, we're going to use some time frequency localized smooth bands. So these are going to be smooth functions that, to the extent that is possible, they cannot be perfectly localizable in time and frequency, but to the extent that is possible, we're going to have very good localization in both domains, both in time and frequency of the function. Unlike these functions, which are perfectly localized in terms of frequency, they only have one frequency, lambda, but they are not, of course, they are spread. Think of this as really sine and cosine. The real and imaginary part are sine and cosine. They are spread all over the real line, let's say, right? So these function phi are going to be of short duration, and they're going to have only a few number of frequencies, or a small interval of frequencies. Okay, so these lead to Elliptical pair theory and wavelet decomposition. And the situation is the following. So the Fourier transform has a very important property that essentially is an isometry. It's not quite for the way I define the Fourier transform. There is a 2 pi that we had to pay for, but other than that, it's essentially an isometry in L2. But that's very far from being true. I mean, there's nothing similar to that in LP. So it doesn't preserve the LP norm. And so we would like to be able to compute the LP norm of a function using information from the Fourier transform. And so there is a substitute for what the Fourier transform cannot be done, and is provided by this Leibniz-Pelli decomposition. And the idea here is to start with the function. Let's look at this picture first, and then we go back to the equation. So we start with a function like this, the black one that lives on an interval away from the origin, kind of a smooth version of the function psi I used before in that cartoon about filtering. And then I'll now start to dilate this function, preserving the L1 norm here. But as we dilate, because of the effect of the Fourier transform dilating, what we produce is that this function, since it meets the origin, it really gets stretched in this way and moving away, right? And so as we take C over 4, C over A, and so on, we move this way. And on the other direction, we move toward the origin. Well, and we can do that in such a practical way that when we add all these functions, you see some of them, most of the time they don't overlap, but they overlap on a piece, right? When they overlap, we add them together and they add up to 1. And there is a square here, which is not, it's just for technical convenience, but just think as it's a partition of unity, right? A very particular partition of unity. Why do I exclude C equal to 0? Because since we started with a function that misses the origin, misses C equal to 0, no matter how we dilate it, either way, we're never going to cover that point, right? So everything else add up to 1, but at the origin, the sum of all these functions will still be 0. That's just one point. It's not relevant for when, especially when we work with function, let's say in L2. So that is not a complication. And so an advantage of this is, and I have been referring to LP, and so this is what I mean by LP, is a space of function, measurable function whose pth power, and there is a typo here, that should be 1 over p. Sorry, I apologize for that. When you form this integral is finite. And the nice thing is that you can recover this LP norm by convolving, by looking at each of these pieces, which are called the Leibniz-Pelli pieces of the function. So remember, when we take the Fourier transform this, we just multiplying the function by one of these dilation of phi. So each of these pieces has a very well localized place on the Fourier transform side. Now, if you've never seen this, you may think, what kind of crazy idea is this? Again, there's a 1 over p, there are no p. This is not such a complicated expression. This looks like a horrible, complicated expression. But it's not such. The advantage of this is that it separates, it builds in some orthogonality in between all these pieces that can almost be treated independently of each other. And that facilitates a lot of the analysis that takes place. And as I was saying, these pieces has such a localization, so they live essentially with where C is of the order of 2 to the nu. And so one can prove that essentially when one takes the derivative of one of these pieces, and taking derivative is something we're going to be doing a lot. That's why I come back to this remark. That's essentially like multiplying the original piece by 2 to the nu alpha, right? So these become, again, something very useful when studying derivative. And also a nice thing is that these are kind of a universal characterization of many function spaces. So if you are familiar with Sobolev spaces, that means are the function, for example, LSP means the function which have S derivative, the function and all its derivative are in LP. And that can be also characterized in a similar fashion are in this new component here, right? That capture this S here, capture the number of derivative or regularity that the function has. So these can be further discretized, and this function, when we look at this function here, that doesn't oscillate much because it has all frequency only on an interval of length 2 to the nu. So we can essentially sample that function or recover it. It won't oscillate much on an interval or length 2 to the minus nu, since there only has certain number of frequency. The reciprocal of that is the period of the function, so to speak. And so the function will not oscillate much on that interval. So remember, we put that square right in the formula of Leibniz-Pelli. That's where this appears now. We want to convolve the function with phi nu twice, because the sum of these, the sum of the square of this function phi nu add up to 1. So this is nothing. This is just multiplying the function by 1. But now this is called the Calderon reproducing formula. This allows us to discretize this further and lead us to what we call the wavelet or a wavelet characterization of functions. So I need to introduce to you here the dyadic cubes. So for think of the plane, just to fix idea. For every scale nu, we divide the plane into squares that are of sine length 2 to the minus nu, and then we translate that to all the integer position, or rather dyadic integer position 2 to the minus nu k. So in general, in n dimension, 2 to the minus k represent what we call as the lower left corner of the cube, and the size of the cube is 2 to the minus nu. So for each new phi, we provide a covering of the whole space, and then there is some hereditary property of this cube as we change nu. So each of these, for example, each of these square will have 4 child, as we call it, inside, and then each of these square will have 4 of these smaller one, and so on. And they don't intersect except on the boundaries among themselves, and they provide at each level a covering of the space. So through this discretization, and the expression look complicated, you know, it's not really important for the purpose of this talk, we can further characterize LP spaces, and not just LP spaces, a whole variety of spaces. And the important thing here is that, again, look, this is just given by the coefficient, right? So these are fixed things, the baryon nu and k, but you know, this is the characteristic function of each of these cubes or square if we are in 2 dimension, and just the coefficients here, the correlation between the function and one of each of these wavelets is what give us the information. So here is what the wavelets look like, this short duration smooth band that I was talking about before. And so each of these coefficients represent how well this function f correlate with one of these generic forms at a scale and at a particular scale and position on space. So for each nu, we dilate these things. So as nu is, you know, smaller, bigger than is positive, let's say, you compress the size on where the function lives, but you stretch in this direction so that you preserve the energy, you preserve the L2 norm of the function. And then you move these at deeper in position 2 to the minus nu k. So you take one of these waves and you wave pack it and you just move it at different position and see how well it correlates with the function. And that is used to characterize the function. Okay, so next I need to give you a very quick introduction to what Calderon-Simon operator are. And this is something that it will, you know, we can spend a lecture on each of the operators that I will mention, but just to give you an idea, the germ of this is, it goes back to Calderon and Simon and looking at the solution of the equation Laplacian of u equal f, and n larger than 3, because, you know, if I took n equal to 2, I will have to change this expression. And so for simplicity, let me just fix n larger than 3. And you can represent the solution through this integral. You are integrating the function fy or convolving with this kernel, and you integrate it and get x minus y at the power n minus 2. Well, if this is supposed to solve this equation, that means when I take 2 derivative of u, you know, I want to see what happened to this expression. So imagine taking 2 derivative of the function u and formally moving those derivatives inside the integral. They only depend, the only dependence, oops. Okay, sorry about that. The only dependent on x is here. So when you take 2 derivatives, every time you take a derivative of this expression, you're going to increase this power by 1. So when you take 2, what you're going to get is something that behaves like x minus y to the power minus n, or 1 over x minus 1 to the n. And that is, it's very scary because, as you know, This is a function that is not locally integrable. So as x approach y, this blow up. It's not locally integrable. It's also not integrable at infinity. It decays, right? It's 1 over x minus y. X gets far away from y, that decay, but it's not enough to decay fast enough to make this integral finite. So it has to be interpreted in a proper sense when you take two derivative, and that led to the study of what nowadays are called Calderon-Sigmund operators. So, and these are operators that essentially behave like those. So here are a few examples. Perhaps the most typical one is in one dimension, the Hilbert transform, which is f of y over x minus y. And this has to be interpreted as a principal value singular integral so that we can make sense. But we can always take the Fourier transform and then inverse. So if I take the Fourier transform of this function, one can show that is, remember, convolution goes to a product of two functions. The product that you need to multiply by is just the function signal of c. And then I compute the inverse Fourier transform to recover the function. So in these two examples, this is the version of the Hilbert transform in higher dimension, which are the Riesz transforms. The expression, again, on the Fourier transform side is easier to understand, and it gives us an alternative representation of the operator we have. These are more complicated operators that cannot be written in this way because they are not convolution one. But they are also great important in analysis. But as I say, it will take a lot of time to talk about them. I just wanted to show you as two other examples, typical example of Calderon-Sigmund operator. So the characteristic feature of this operator is that they are indeed bounded in L2. If they are bounded in L2, then and they have this regularity. So every time you take a derivative, you increase this negative power of x minus y, then just being bounded in L2 means that the operator are bounded in LP. Now this is something very nice because there's no guarantee that for a linear operator bounded in L2, it will have to be bounded in any other LP. But it is the case for Calderon-Sigmund operator, provided you have this amount or something similar to that regularity. So the big question is, when are these operators bounded on L2? And again, for convolution one, so when the kernel is just a function of x minus y, then again, we can use the Fourier transform. And remember, again, it transforms convolution into multiplication. So this function m is the Fourier transform of k. And then for this to be in L2, require the Fourier transform to be in L2. And for a function in L2, multiplied by another will be in L2, one can easily realize that the function has to be essentially bounded. It has to be in L infinity. So this is an if and only if relation, and it's very easy to establish. However, there are operators that are non-convolution. And so in that case, we cannot use the Fourier transform in this straightforward way. And this was a very interesting problem open up for many years until the mid-80s when it was resolved by David and Journet in a very elegant way, and saying that an operator with a Calderon-Sigmund kernel is bounded in L2 if and only if the operator and its transpose, T star is the transpose operator, when computed on this character function, and then we take the VMO norm of this function. Here I have the definition of VMO. If you haven't seen it, this is the space of bounded mean oscillation. You look at the difference between the average of the function minus its average on every cube, and that needs to remain uniformly bounded. If those are bounded by a constant C, then the operator is in L2. The reason that is called the T of one theorem doesn't appear at all here is that the original version of David and Journet require a property on T on the function 1 and some other weak continuity property. However, they also prove in this alternative form where T and T star on all the characters needs to be bounded in this space BMO. And I like this version a lot because I like to think of this function, the exponential, as pure tones. And this is, again, very nice that it's telling you essentially, of course, they are far from being a basis or anything like that. They are not even in L2, this function, but in a way it's saying that all you need to do is to understand operator is to understand it on some kind of basis, as we do in linear algebra, right? That's all what we need to know to understand a linear operator. And in this case, we're talking about boundedness, so it gets a little more complicated. But I like to think that the way I always express this is that to understand the music played by T, so think of these are pure tones, so each note, to understand how the music, so the music will be how it acts in L2, the music played by T, you really need to understand how to play each note, right? Otherwise, you cannot play the song that T represents. Anyway, that's one way to think about it. So this can be proved by some almost diagonal estimate. And again, I didn't want to lie, so I write the correct expression. It's very complicated, but what I want you to see is this thing that we were talking earlier on about, and this is what really quantify what do we mean by obtaining an almost diagonal matrix. Well, look at these two expressions, and I think it's easier to look in this case where a function phi nu k lives in a QQ and the function phi mu L lives in a Q mu L. These are two different dyadic cubes. Now, look at this expression that is easier to understand that they are equivalent, trust me. So what this says is that when can this be very small? When, I'm saying that if nu and k and mu L are very different, we should get something that is essentially zero or very small. So this metric is not diagonal, but it's what we call almost diagonal. So when can that happen? When is this psi going to be small? Well, there's two factors, right? So probably that's going to be small if either of the factor is very small. Well, how can this factor be small? Well, this could only be small if Q is much larger than Q prime. In other words, if the size of the QQ is very different from Q prime, that means that these functions oscillate at very different scale. So when one oscillates at a very large scale and the other a very small one, then they are invisible to each other, and this will be very small. The other possibility is that maybe this factor is not small because the oscillation is similar for both factors, but how about this term? When is this going to be small? Well, this is going to be small when this diameter is very large. And when is the diameter of the QQ and with the union of Q prime going to be very large? When the cubes, remember for the fixed nu, so if the nu were the same, they're going to be far, they don't intersect unless they are adjacent, they just touch on the boundary. So this is going to be very large if the Q are very far apart. So in other words, if the frequencies at which the wave oscillate are very different, or their position of this packet of wavelet are very different, then this expression is going to be very small. Okay, so this, if you attended this morning, you saw this picture again. So the reason for that, why is this really possible is that because waves that have very different frequency are really not, are invisible to each other. They don't affect each other much. And I showed this morning this cartoon, right? Imagine instead of wave, they are represented by balls of different size. And if you have a crack on the floor, and you roll a basketball ball, it's just going to go over it because the physical dimensions are so different. In this case, we can think the level of oscillation are so different that they ignore each other. However, if their physical dimensions are comparable, like when you roll a ping pong ball, then it's going to be scattered by the crack, right? There's going to be some interaction. So the thing is that this Calderon-Sigmund operator transform wavelet into things that look very much like a new wavelet. So they're not exactly the same. They're objects in mathematical molecules. But when you apply T, a Calderon-Sigmund operator, to one of these wavelets, you get something that looks much like a wavelet oscillating at the same frequency and located at the same position. So think again that you have one wavelet that oscillates at a very, large scale, the red one, and think one that oscillates very fast on this particular location. Of course, if they are very far apart, I didn't even consider that case, but if they are very far apart, if they are located very far away, since this function die away very quickly, the integral of one against the other is always going to be very small, right? It's going to be practically be zero because they live very far apart. Now, when they overlap, and let's say one oscillates much faster than the other, think in this term. The red function has very low oscillation. So for practical purpose, this function is essentially like a constant for the eyes of the blue highly oscillating wave. So the red one is essentially constant, but the function, the blue one, has a lot of oscillation and it has cancellations, right? Probably their integral is 0 and maybe some moment are 0. So if you integrate something that is essentially constant against something that has mean 0, then you get something very small. Of course, this needs to be properly justified and quantified, but that's the main idea behind why this wavelet diagonalize Calderon-Sigmund operator. Okay, how about bilinear? Because I need to get to bilinear Calderon-Sigmund operator. So, you know, looking at this expression, I'm doing something that looks kind of silly. I'm taking the function f and g. I'm writing f and g as the inverse Fourier transform of their Fourier transform. And then I put the two integrals together. Of course, the two variables are separated. Just this is nothing, right? I just write them as the inverse Fourier transform of their Fourier transform. And of course, one depends on the variable c and the other on the variable eta. Now, this gives me a motivation to look at other bilinear operation, like the product of the function. I can take the derivative of the product of the function. And doing a similar analysis, I get to an expression that now is similar. Now I cannot separate so easily the two integrals, but still I have a function of c, a function of eta, this complex exponential, and then a symbol or a function here that depends on c and eta. So moreover, if we define fractional derivatives, so if we, now s could be any number, not just an integer, and I define this to be the Fourier transform of this fractional derivative to be this expression here, then one can also show that the fractional derivative of f times g behave in this, I can write it in this way. So this gives me a kind of generic way to write certain bilinear operator in terms of the Fourier transform of the functions that are the entry of the operator. And we can do this in a more precise way and realize that if we split this integral where one of the variables is bigger than the other and the other piece, you can rewrite this in a way that involves an operator T1, an operator T2, and all the derivative fall in F, or all the derivative fall in G. Now, you saw the words Leibniz rule in the title of the talk, and this already starts to look like Leibniz rule. If you take the derivative of the product, let's just say one derivative of the product, then we all know you will have the derivative of f times g plus f times the derivative of g. Well, here is a lot more complicated, but it's kind of the same idea. And what are these T1 and T2? These happen to be some operators that we call bilinear Calderon-Sigmund operators. So more generally, if I have a symbol that it could even depend on x, again, these are technical aspects. I don't want to spend time on that. It has to be some condition how they behave. Whenever you have this property, then the operators are represented also by these singular integrals, where now the kernel is like the kernel of a Calderon-Sigmund operator, but in double the number of dimensions. So, now think that this lives in R2n, and this looks like the Calderon-Sigmund kernel of a function that is linear in R2n, but this is bilinear because we split the variable in this way. And by now, the theory of this operator it's well understood by work of all these mathematicians that I include here. And then we look at Grafakov, we prove a theorem that is the equivalent of the T1 theorem. And so now there are two transposes of a given operator, the ones that you obtain by switching the variables, freezing one variable and applying the transpose on the other. And again, the condition is that when you compute on the complex exponential, they are uniformly bounded in BMO. So this is something that is easy to, or at least in some example, easy to compute, and it's a way to have a criteria for when an operator is going to be bounded in the product of all these LPQ spaces. Now, let me just skip this because this is just a nightmare. Just to look at it, I couldn't even find a way to write it. I had to use small letters so that it fits. But this is how we will quantify these from the point of view that saying this is almost diagonal. So again, we can do an analysis similar to what we did before, that for different values of this parameter, different factors in this expression are very small. And of course, this can be done multilinear, and imagine it will be even more horrible to look at, but the notion is similar to, that's where I went in detail through the linear one. Okay, so I think I'm gonna skip that part. But let me say that we have, going back here, we have this symbol here. Well, when this symbol is just a function one, this is just the product of functions. So in particular, we can use this to study Leibniz rule, or in other words, the derivative of functions. So in this case, we are measuring the derivative. Remember, this norm means the value of S derivative in LR, and we can show that if you want to estimate S derivative in LR of the product of two functions, what you need to do is like in Leibniz rule, you take all the derivative in F, or you take all the derivative in G and estimate the corresponding expression. And again, this estimate had a very long history. It go back to original work of Cato and Ponce and Chris and Weinstein, and now it has been studied for many different exponents. And the last result was by Bourgain and Lee that addressed the case when P and Q and R are all infinity. So all these estimates are based on L infinity. Okay, and many other results. All the name I can think from the top of my head. I'm sure I missed some, and there are a lot of literature in this regard with many subgroups of these individuals. So I won't have a chance to talk about it. But I want to do this in the context of mixed Lebesgue spaces. So let me quickly remind you where mixed Lebesgue spaces are. So they are given by an expression of this form. There's two variables, and here we choose to be T a one-dimensional variable to represent time, and X and space variable n-dimensional one. So we take a different LP or LQ norm in the different variables. So we first take an LQ norm in X here, and then we raise that to the P, and we take the LP norm of the corresponding function. So as you can see, we cannot switch this order in general. And so we are measuring in terms of LP in a different way this function with respect to the different variables, right? And there is a long history in harmonic analysis going back to some Argentinian mathematicians, Benedek, Calderon, and Panzone, and then important work of Rubio de Francia, Ruiz and Torres, Fernandez, and so on. So, essentially all what we need to know about these spaces is known. So why the interest of this? Well, because in many situations, especially dealing with a situation in partial differential equation with physical quantities that depend on time and space, you need to measure different psi in each variable. And so that is where this norm naturally appears. Now, we could have split this in any other form. I could have, let's say, if n plus 1 were 5, I can take two dimensions in T and 3 dimensions in X. And all what I'll talk about will be the same. But that will be just a generalization. Really, the meaningful or important case is when T is time and X is space. And there are, I'm trying to prove Leibniz rule estimate in this context. There were already some by Kenya, Ponce, and Vega, written in a different form. So rather than estimating the derivative of F times G, they estimate the difference between the derivative of F times G minus F times the derivative of G minus G times the derivative of F. Now, one thing that I want to point out is that their derivative in this case only involve differentiation on the space variable, or rather in this case, when you take the Fourier transform, is this n-dimensional frequency variable that appear. No derivative on the time. So what we wanted to do is to try to prove estimate of Leibniz form for derivative that involve really all the variables, both T and X. And that is the new part on what I talk about in this talk, that the new result that I want to present. So again, what is the fractional derivative? Now in Rn plus 1, but it's the same as before. We take the variable to the power s, and that's the definition of this fractional derivative s. S is any positive number, it doesn't have to be an integer. And so when you declare that the fractional derivative is the function that when I take the Fourier transform, I get to multiply this function by the s power of the variable c, which I will often divide into a one-dimensional C0 and an n-dimensional Cn. So this is nothing that the same fractional derivative I defined before, but the fact that we are looking at mixed norm, we take a norm in one variable and then another norm in the other variable, complicate things technically substantially, because I cannot just arbitrarily switch the order of these integrations. Okay, so again, this is something very technical. One important tool that we use in this context is the vector value version of the Hardy-Litigal maximal function. We don't need to talk about that. Only for those of you that are familiar with this. And in fact, using this vector value theory, one can show that this is again the convolution with the functions phi, this Litigal Pelli-Pizzi. One can compute the LPQ norm as a Litigal Pelli norm, similar as we did. Of course, if we put P equal to Q, this is just LP in n plus one dimension. But what these expressions say is that we can compute that still when P is different than Q. So again, consider this bilinear operator with some technical condition. What we will show is that if we take S derivative of an operator like this, in particular the one in which M is 1, then you can estimate S derivative in the full variable T and X of this operator by the derivative in one function and then putting all the derivative in the other. And this is what are referred to again as Leibniz type rule. Okay, so our first result were with a former pseudoman, Erika Ward, that but we needed to restrict a range of exponents. So that again is something rather technical that I don't want to spend too much time on it, but it didn't work in the general context. So we needed to do something else. Now I want to mention that there are other results of this type by Benea, Muscalo, and Di Plinio No. But notice here that instead of taking a combined derivative of the product, they take an iterative derivative. So first they take derivative in X and then the derivative in T, while we're taking the full fractional derivative simultaneously in all variables, right? So that's a big difference. And there's no relation really between these two estimates. None imply the other. They're just different. They look similar, but they are different. Okay, let me escape this thing about HP. So what is the result? Well, we show that when the symbol has this condition, the technical condition, then we can prove that Tm applied to a product of functions, so not a product, applied to Vn, this bilinear operator is bounded in this range of exponent. However, what do we do when we apply the derivative of this operator? How do we apply? Remember, I was trying to show this for derivatives. So M now I apply this operator and then I take S derivatives and I get this Leibniz rule. And the reason that this is work, and again, I won't be able to go over this, but is that we are able to decompose this operator into two ones. One that acts on all the derivative in F and then G, another on F and all the derivative in G. And these operators are now of order 0, as in the previous theorem. And so they are bounded. And so that's how we obtain the expression we were trying to get. In particular, when we set the symbol M to be the function 1, that's probably the only interesting case for this talk. We now recover, or not recover, we establish now the Leibniz rule, but with mixed Lebesgue norm. I think because my time, I want to leave a chance for some question, I'm going to stop here and Harvard stop sharing, and I'll be glad to answer any question you may have.
So, any question or comment? The almost orthogonality, the famous paper by Misha Kotler, is kind of
Yeah, it's interesting. It's not really the same because Misha Kotler paper, famous almost orthogonality lemma, is about dividing the operator as a sum of operators, which don't interact much with that. But it's behind. I mean, it's a great question because it's not really, in a way, it's a substitute for that. For many years, people try to do something similar in LP without a satisfactory way to do it. And what we are doing here is we are not dividing the operator, but rather dividing the functions on which the operator are. But that notion of almost orthogonality is the same, right? Yeah, that's a very good point. And of course, Misha Kotler is still is. It's not around here, but such a dear person for Wilfredo and I that we always like to.
Okay. Well, I think, Rodolfo has a meeting at 4 sharp, so I think we better stop here and thank you again. So thank you for all the effort and your time. And well, I will invite you to a restaurant here to
we'll get together sometime.
Yeah.
And thank you again for inviting me. And I hope I know I went a little fast today, but the second talk, I think, but I hope I communicated some of what we're trying to do, and I hope I get to see you sometime in the not so long future in person. I'm meeting you. And have a great day and
something.
Bye-bye.
Bye-bye. Take care. Okay.